Welcome to the deep dive. You've given us your curiosity and a pile of fascinating sources, and we're here to pull out the essential insights fast. Today, for you, our listener, we're tackling a really interesting intersection in modern computing. It's about these surprisingly similar ideas popping up in, well, three different areas: cell-based architectures, flow-based programming, and agentic systems. You want to get a solid grasp on this without getting bogged down, right? And that's exactly what we're aiming for.
It's true. I mean, when you first look at cell-based setups and then flow-based programming and then these agentic systems based on your materials, they might seem like completely different worlds.
Yeah,
But
exactly.
what's fascinating and what the sources really bring out is how these different approaches keep landing on some very similar fundamental principles: modularity, interaction, autonomy.
Ah,
These themes just keep recurring.
absolutely. So we're going to explore how cell-based architectures bring this incredible resilience and, the ability to scale massive systems. Then we'll look at flow-based programming, which offers a really unique perspective by focusing much more on how data actually moves and changes.
The data-centric view, yeah.
And finally, we'll dive into agentic systems where you have these, well, intelligent, autonomous pieces working together. The real kicker, like you said, is seeing how these seemingly unrelated fields are all kind of grappling with the same core concepts. Okay, let's dive in. Starting with cell-based architectures. What's the big picture there?
Well, the core challenge that cell-based architecture really tackles is the sheer complexity of operating these really large distributed systems. The fundamental idea is to take that massive workload and break it down
Break it down how?
into completely self-contained independent units. We call them cells.
Right, and the immediate win there is resilience, isn't it?
Yeah.
One of the sources used a great analogy like the watertight compartments, the bulkheads in a ship.
Exactly. That's a perfect analogy.
Right.
If one section gets breached, if one cell has a problem, the whole system doesn't sync. And to make this work in software, you need a few key pieces. First, obviously, the cell itself. It's a fully independent instance of your application with all the resources it needs: compute, storage, everything.
Got it. Self-sufficient.
Then you have something called the cell router. And this is critically an incredibly streamlined component. Its job is just to direct incoming requests to the correct cell,
How does it know which cell?
based on something called a partition key. Think of it like a zip code on a letter. It ensures the request gets routed to the right local cell based on, say, a customer ID or maybe a resource ID.
Okay, simple routing.
And finally, there's the control plane. This handles all the background administrative stuff: provisioning cells, managing deployments, monitoring, that sort of thing.
So the modularity comes from these truly isolated cells. They operate independently, which means, like the ship bulkhead, if something goes wrong in one cell, it's contained. It can't easily cascade and take down everything else.
That's the blast radius concept they talk about. You're shrinking it dramatically.
Plus, because they're self-contained, you can scale each one up or down based on its specific needs, right? And even deploy updates to just one cell without touching the others.
Exactly. It's like having, as you said, a fleet of smaller, more maneuverable ships instead of one giant vulnerable one. That independent scaling and deployment is a huge operational advantage.
Okay, so they're isolated, but systems often need parts to talk to each other. How do interactions work between cells?
Yeah, good question. They interact through well-defined APIs and messaging protocols.
Mm-hmm.
But, and this is a critical insight from your sources, the design of that cell router is paramount.
You mentioned it needs to be simple.
Absolutely. It has to be as simple and efficient as possible, the thinnest possible layer. Otherwise, it risks becoming a bottleneck, or worse, a single point of failure itself.
Right.
And the choice of that partition key, whether it's customer ID, region, resource ID, whatever that choice, has a profound impact on how often cells actually need to talk to each other.
So you want to choose a key that keeps most of the related work within a single cell.
Precisely. The goal is to maximize that self-sufficiency within each cell and really minimize those cross-cell dependencies and interactions.
Makes sense. And the autonomy aspect, where does that come in?
Well, it comes from each cell managing its own operation and, crucially, its own state, its own data. This independence has some really powerful benefits beyond just failure isolation,
Like what?
like making deployments much safer. You can do canary testing, roll out a new version to just a single cell, monitor it carefully without risking the entire system. Testability also improves because you can often test a cell in isolation.
Yeah, that sounds incredibly useful. The source material gives some compelling real-world examples of this. Slack's migration is a big one, right? Moving to a cell-based architecture on AWS.
Yes, That's a great illustration. They were facing these tricky intermittent failures, these gray failures, and wanted better resilience against things like entire AWS availability zone outages.
So how did cells help?
They essentially made each availability zone, each AZ, its own isolated back-end deployment effectively, a cell. All the necessary services and data for that cell were contained within the AZ.
Okay.
And what's really insightful about Slack's setup is how they leverage technologies like Envoy and XDS for that routing layer.
Yeah.
This allowed them to very, very quickly, the source says, under 5 minutes, divert traffic away from a failing AZ, a failing cell.
Wow, 5 minutes to drain an entire AZ? That kind of rapid failover is huge for resilience.
Absolutely. It dramatically improves their services resilience against those kinds of infrastructure problems.
And AWS themselves obviously promote this. They offer guidance, right? There's that GitHub sample, guidance for cell-based architecture on Oz, and a sauce workshop mentioned.
Yeah, both of those show you how to actually build these things. Create the isolated cells, partition the data effectively, implement that crucial cell router. They really emphasize shrinking that blast radius and achieving that highly desirable linear scalability.
Linear scalability meaning?
Meaning as your overall load grows, you just add more cells. Ideally, your capacity grows linearly with the number of cells you provision.
Nice. And the source mentions Flickr doing something similar even earlier, sharding user data across clusters.
Right. While they might not have called it cell-based back then, Flickr's approach of federating their system by sharding user data across different database clusters aligns perfectly with that core principle of data partitioning that underpins modern cell-based architecture. It's an early example of the same thinking.
So it feels like cell-based architecture is almost like the next evolution beyond microservices in a way. Microservices break down the application, but cells add this crucial layer of structural isolation and managed interaction, especially at massive scale.
That's a very insightful way to put it, yeah. It's taking the benefits of smaller services decomposition and then applying a higher-level organizational pattern to manage them effectively, particularly managing failure domains and dependencies. It addresses that microservices sprawl problem you sometimes hear about.
And as we've said, that selection of the partition key is just absolutely fundamental. It dictates the communication patterns, the data locality, basically the effectiveness of the whole isolation strategy.
Couldn't agree more. Get the partition key wrong, and you could end up with tons of cross-cell chatter undermining the whole point.
And that emphasis on the thinnest possible layer for the cell router keeps coming up. It really can't become this complex beast. The source mentions strategies like using standard load balancers or simple request forwarding, or even DNS-based routing to keep it lean.
Exactly. Keep it purely as a traffic director, no business logic, minimal state. And there's another interesting layer mentioned, the socio-technical one.
Conway's Law.
Precisely. The idea of aligning team responsibilities with these cellular boundaries. It's considered a more advanced pattern, but it makes a lot of sense. It allows teams to truly own and evolve their part of the system independently, reinforcing that autonomy at an organizational level, too.
That's fascinating. Okay, so that's cell-based architecture, isolation, resilience, managed interaction at scale. Let's shift gears now and explore a really different way of thinking about building applications. Flow-based programming.
Yes, FBP. This was quite different.
It has this really interesting data factory feel to it, doesn't it? Instead of focusing on a step-by-step control flow, do this, then do that, you're essentially building a network of these self-contained black box processes whose main job is just to transform data as it flows through the system.
Right. What's really fascinating here, and it's a key shift, is the central role of the data itself. In FBP, applications are viewed as these interconnected networks of asynchronous processes. The key is these processes don't directly call each other like functions normally do.
How do they communicate then?
They exchange data, but only through explicitly defined external connections. Think of like workstations on an assembly line, passing parts between them via conveyor belts.
Okay, so the core ideas are these reusable black box processes. You have the data itself moving around in chunks. Information packets, or IPs, the source calls them, and then the connections, which are like those conveyor belts, pathways linking the processes. And these connections have a fixed capacity.
Yes, that's a crucial point. They're typically bound in buffers, fixed capacity pathways. It's a component-oriented approach, but the coupling between components is very loose.
Yeah.
It's primarily data coupling. Processes only need to know about the format of the data they expect to receive and the data they produce.
And the network itself, how all these processes are wired together, that's often defined externally. maybe even visually.
Exactly. That's a very powerful aspect. The structure of the application, the flow, isn't hard-coded within the processes themselves. It's defined separately.
So the main building blocks, you've got the processes, the reusable code doing the work. You've got the IPs, the data chinks, the connections or wires with that defined capacity, and then ports, which are like the input and output sockets on the processes.
Correct. Named attachment points, input ports, and output ports where the connections attach. And finally, there's usually a scheduler component that manages when the process is run, based on the availability of data and the network definition.
That fixed capacity of the connections you mentioned, why is that so important?
It's actually quite brilliant. It provides what's called implicit back pressure automatically.
Back pressure.
Yeah. If a process downstream in the flow is running slow, maybe it's doing complex work or waiting for an external resource, the connection leading into it will start to fill up with IPs because it has that fixed capacity.
Like a conveyor belt backing up.
Exactly. And because the connection is full, the upstream process that's trying to send data to it will naturally pause or block because there's nowhere for its output IP to go. It's a built-in, very elegant mechanism for handling different processing rates across the network without explicit coordination code.
That is clever. It prevents faster processes from overwhelming slower ones.
Precisely. Yeah. And the modularity in FBP really shines through in the reusability of these process components. Because they're black boxes, communicating only through data on their ports, you can wire them up in all sorts of different configurations to build completely different applications.
The source mentions visual programming tools like Node-RV, which really makes this tangible. You can literally drag and drop these process nodes onto a canvas and draw wires between them to build a workflow.
That's the core of what the source calls configurable modularity. You build these reusable components, and then you configure the application by defining the network externally. Often you can also configure the components themselves using what are called initial information packets, or IIPs.
IPs?
Yeah, basically parameters or initial data that get sent into specific ports when the network starts up. It makes the components even more flexible and reusable, very much in line with modular design principles.
So interaction in FBP is fundamentally message passing, isn't it? It's all about these asynchronous processes communicating by sending those IPs through the bounded connections via the named ports.
That's it. It's a very data-driven form of interaction. A process only activates and does its work when it receives the necessary data, the IPs, at its designated input ports.
The data pulls the computation along, rather than a central control flow pushing it.
Exactly. The arrival of an IP at an input port is the trigger for a process to execute. And because those connections have that defined limit, you get that automatic back pressure we discussed, which helps prevent any single part of the system from getting swamped.
And the autonomy in FBP, where does that come from?
It comes from the fact that these processes generally run independently and asynchronously. They don't have to wait for each other explicitly. A process just waits for its input IPs, performs its transformation when they arrive, and then sends its output IPs out through its output ports whenever it's done.
And it doesn't necessarily know or care who sent the input or who receives the output.
Largely, no. It just cares about the data format on its ports and the connections defined externally. What's also really interesting, and mentioned in the source, is the potential for language independence that FBP offers.
Meaning different processes in the same network could be written in different languages?
Theoretically, yes. As long as they can agree on the data format of the IPs being passed and can interface with the FBP scheduler and connection mechanism, you could potentially mix and match components written in, say, Python, Java, or even older languages. The source mentions the Instance ET framework for navigation software as a practical example, showing this kind of autonomy and parallelism in action.
That language independence is a really powerful idea for integration, isn't it? You could potentially connect a legacy COBOL system to a modern machine learning component using this data flow approach.
Absolutely. It opens up possibilities for integrating diverse, maybe even previously siloed systems within a single coherent FBP framework.
The source provides some fantastic real-world examples of FBP, AMPS, that system used by a Canadian bank processing huge data volumes. It ran for nearly 40 years.
Yeah, isn't that incredible? Almost 4 decades in production really speaks volumes about the potential robustness and reliability of this approach when implemented well.
It really does. And then you have Node-RED, which you mentioned. It's become super popular recently, especially in IoT, home automation, things like that.
Very popular.
The case study with abrasive technology, using it for machine automation and monitoring in harsh environments, that really illustrates how these modular nodes and the visual data flow can be applied in very practical, demanding, real-world scenarios.
It shows the visual aspect,
Yeah.
the modular nodes, the interaction via data flow, all working together to control robotics in a tough setting.
And Apache NiFi is another big one in this space, right? A
Yeah.
data flow management platform, also with a visual interface.
Yes, NiFi is widely used for data integration and ETL tasks.
The retail workflow example they described is great. Collecting transactions from Kafka, enriching them with data from a PostgreSQL database,
Right.
transforming the format to Parquet,
Standard data engineering tasks.
and then routing the data to different Azure Blob storage containers based on, say, the region or the product type. It really highlights how you can chain together these modular processors, as NiFi calls them, to build quite sophisticated data pipelines that are still relatively easy to understand visually.
That retail example perfectly showcases the modularity. Each processor does one specific thing. It shows the interaction via flow files, NiFi's term for the data packets. And it highlights the autonomous operation. Each processor just does its job as data flows through the defined paths.
And the source mentions other, maybe more niche examples too, like solving the Telegram problem, batch updates, even running ML inference inside network switches with something called Florist.
Right, it shows versatility.
Yeah.
FBP isn't just for one type of problem. It can be applied to synchronization problems, like the Telegram example, traditional batch processing, real-time stream processing, and even these specialized edge computing scenarios.
So FTP really represents a fundamental shift in thinking, doesn't it? Moving away from imperative, step-by-step control flow, and instead focusing on describing how data should flow and be transformed as it moves through a network of independent processes. The source says it requires a change in thinking.
It absolutely does. It's a transition from a control flow-centric view to a data flow-centric one. And that externalized definition of the connections, how things are wired together, is incredibly powerful for component reusability. You can essentially unplug and replug components in endless combinations.
That sounds amazing for flexibility.
It is. But, as your sources rightly point out, it also introduces a challenge. Managing these potentially large and complex network definitions. How do you visualize, debug, and maintain a complex graph of interconnected processes?
So good design and good tooling become really important.
Essential,
Yeah.
especially visualization tools. And those emergent properties, we talked about the implicit concurrency because processes run independently, and the automatic back pressure from the bounded connections. Those are such valuable benefits that come almost for free from the architecture itself. It's a very natural way to handle parallelism and flow control.
Well, so powerful reusability, but you need good tools to manage the complexity of the network definitions.
Exactly. And that language independence really does open up interesting possibilities for integrating diverse systems, maybe even leading towards some kind of common FBP protocol in the future, as the source speculates.
Fascinating. Okay, let's move on to our third paradigm, one that's been getting a lot of attention lately, especially with all the progress in AI agentic systems.
Ah, yes, agents. This is definitely a hot topic.
So agentic systems, this is all about using autonomous or perhaps semi-autonomous agents. These are entities that can perceive their environment, make decisions, and then take actions to achieve specific goals.
That's the core idea.
The source helpfully breaks this down a bit, distinguishing between, let's see, basic AI agents, then agentic AI, and also multi-agent systems, or MAS. What's the difference there?
Yeah, that categorization is useful because the term agent gets used broadly.
Yeah.
So AI agents in this context tend to be more purpose-built for narrower, well-defined tasks. Think of things like maybe sophisticated email filters or tools that help query databases or fairly basic chatbots. They often require minimal human intervention, but are typically reactive or adaptive within their specific domain.
Okay, focus tasks.
Then you have agentic AI. This term often applies something more sophisticated, usually involving multiple agents collaborating. They might dynamically break down complex tasks. They often have persistent memory to learn over time, and they operate with a high degree of orchestrated autonomy. The goal is often complex, long-horizon tasks with minimal ongoing supervision. It kind of combines the flexibility of LLMs with the reliability of more traditional programming.
Orchestrated autonomy. We'll come
Yeah.
back to that. And multi-agent systems.
Multi-agent systems, or MAS, is really the broader academic and engineering field that studies systems composed of multiple interacting agents. These agents could be simple or complex, homogeneous or heterogeneous. The focus in MAS is often on the interaction itself, coordination, communication protocols, negotiation, emergent collective behavior, and so on. It's about how the group functions.
Got it. So regardless of the specific type, The key principles seem to be autonomy, acting independently,
And so,
goal orientation, having objectives,
mm,
the capacity to reason and plan, which often involves LLMs these days,
mhm.
context awareness, and that crucial ability to learn and adapt over time.
Yes, learning and adaptation are key differentiators for more advanced agents.
And of course, interaction and collaboration are fundamental, especially when you have more than one agent involved, as in Agentic AI or MAS.
Absolutely. How agents communicate and coordinate is a huge part of agent system design.
Okay, so what are the key components, especially for these more advanced agentic AI systems?
Well, you have the agents themselves, often specialized autonomous entities with unique roles or skills. You have the initial prompts or instructions that guide their behavior. A really important component is memory, the ability to retain information from past interactions. Persistent memory is key for sophisticated behavior.
Right, so they don't start from scratch every time.
Exactly. Then you have tools. These are external functions, APIs, databases, or other resources that agents can use to perform actions in the world or gather information they don't inherently possess.
Like searching the web or accessing a specific database.
Precisely. And finally, you need orchestration mechanisms. These define how the agents interact, how workflows are managed, how tasks are assigned, and how agents contribute to achieving the overall goal.
Okay, so modularity in agentic systems seems to come from having these specialized agents, right? Each focused on a specific part of a larger problem. The source mentions an animal training plan system as an example, decomposing the task into agent-specific roles.
Yeah, that's a good example of task decomposition.
Yeah.
You might have one agent assessing the animal's current behavior, another suggesting training steps, maybe another tracking progress. And you see various architectures for MAS, centralized, decentralized, hierarchical frameworks like LangGraph and Microsoft's AutoGen that provide practical ways to structure these modular agents and their interactions.
LangGraph and AutoGen seem to pop up a lot in the source material. They provide tools for actually building these things.
They do. They offer ways to define agents, their tools, and, importantly, the patterns of interaction between them, how control or information flows in the system.
So interaction in agentic systems sounds incredibly diverse compared to the other two paradigms.
It really is. You've got agents communicating directly, maybe through message passing. LangGraph uses graph edges for this. AutoGen uses a kind of group chat metaphor.
Okay.
You could have orchestration where a manager agent directs the work of others. Both LangGraph and AutoGen support this pattern. Agents might interact via shared memory or a shared state. LangGraph explicitly supports this.
Accessing the same data store, essentially.
Right. Interaction also happens through tool invocation, an agent using an external API. And you can have more structured interaction patterns built on top of these basics, like sequential workflows, conditional routing based on an agent's output, having reviewer agents check the work of others, or even map-reduce style patterns where tasks are farmed out and results aggregated.
Wow, that's a lot of ways for them to interact.
It is. And the underlying architecture of the multi-agent system, whether it's centralized or decentralized, heavily influences which interaction modes are most natural or efficient.
And autonomy. It seems like that's just baked into the definition of an agent.
It's absolutely central, yes.
Yeah.
Agents are fundamentally characterized by their ability to operate autonomously. They are goal-oriented, they make decisions based on their perception and internal state or reasoning, and ideally, they learn and adapt their strategies.
But it's not always complete autonomy, right? The source mentions bounded autonomy in MAS.
Correct. In many practical MAS implementations, an agent's autonomy might be constrained by system policies, rules of engagement, or dynamic agreements negotiated with other agents. It's rarely absolute freedom. The space resource gathering robot example in the source is good here.
How so?
Well, the individual robots, Scout, Gather, Remover, they have autonomy to make their own local plans for moving and acting. But there's also a coordinator agent that handles higher-level coordination and replanning if conflicts arise or the overall situation changes. So it's a blend of local autonomy and coordinated system behavior.
That makes sense, guided autonomy. The real-world applications being highlighted are fascinating. LangChain and LangGraph are being used by some big names. Webtoon Entertainment for story understanding. C.H. Robinson for logistics optimization.
Yeah, the C.H. Robinson example claims savings of over 600 hours per day. That kind of impact gets attention.
Definitely. And the example of a multi-agent city information system combining agents for events, databases, online search, weather APIs, restaurant recommendations, using tools like Tably Search or Open Weather Map, that really shows the potential for composing specialized agents to provide comprehensive, context-aware answers.
It really does. You combine an agent good at database queries with one good at web search, one good at weather data, maybe one that can synthesize the results. And you can answer much more complex questions than any single agent could alone. LangChain and LangGraph are enabling these kinds of composed systems for things like context-aware customer support, intelligent data retrieval, content generation, AI assistance, even financial decision-making support.
And Microsoft's AutoGen has some cool examples too, automating tasks via a simulated group chat between agents.
Right, with manager agents and worker agents collaborating.
And that short-style video generation example using agents for script writing, voice acting via an 11 Labs API, graphic design using Stability AI, and a director agent to pull it all together. That really brings the modularity and interaction to life in a creative context.
It's a great illustration of using specialized agents, each leveraging specific tools, like those external APIs, coordinated to produce a complex artifact.
And it's not just software, right? The source mentions MAS being applied in robotics. Think robot swarms, logistics, supply chain management, smart city traffic control.
Yes, these are classic domains for multi-agent systems research and application.
Even architectural design. Tools like SpaceMaker AI optimizing layouts, hyper-automating design tasks, Zaha Hadid architects using AI.
Yeah, architecture and design are seeing increasing use of agent-based approaches for optimization, simulation, and automating repetitive tasks. And there's a growing ecosystem of other agent frameworks mentioned, Crew AI, ChatDev, MetaGPT, Smithos popping up to help developers build these systems.
So the field is clearly moving very fast. But as the understanding evolves, it seems it's not just about raw autonomy. You mentioned orchestrated autonomy earlier.
Yes, that concept seems increasingly important, especially for agentic AI aiming at complex goals. It's about guiding the agent's independence, structuring their collaboration effectively, ensuring they contribute productively to the overall objective rather than just acting randomly or conflictingly. Designing effective orchestration and interaction patterns is a major challenge.
And the role of tools seems critical too, grounding the agents.
Absolutely vital. Tools, those external functions, APIs, databases, are what connect the agent's reasoning to real-world actions or specific information sources. It grounds their thinking in reality and allows them to actually do things beyond just generating text. A key challenge is enabling agents to identify, select, and correctly use the right tools for the task at hand.
And the source highlights the diversity of agent architectures, centralized, decentralized, hierarchical, reflecting different trade-offs between control and flexibility, depending on the application.
Exactly. There's no single best architecture. It depends on the problem you're solving.
Plus, as these agents become more capable and autonomous, the source mentions emerging risks, alignment faking, self-exfiltration, even self-deception.
Yes, as agents become more powerful, particularly those based on sophisticated LLMs, ensuring they remain aligned with human intent and operate safely becomes a paramount concern. The source rightly points out the need for a systems theoretic safety perspective, looking beyond just the capabilities of individual agents to the behavior of the overall system and its potential failure modes.
That sounds crucial. And finally, the importance of persistent memory and continuous learning seems to be a key differentiator for the really advanced agentic systems.
Definitely. The ability to retain knowledge from past interactions, adapt strategies based on experience, and improve performance over time is what allows these agents to tackle increasingly complex, dynamic, and long-horizon challenges effectively. It moves them beyond simple reactive behavior.
Okay, phew. So we've looked at cell-based architectures, flow-based programming, and agentic systems. Three seemingly distinct approaches. But you said there's an underlying connection, a unifying perspective.
Yes, absolutely. What's truly striking when you look at them comparatively, as the source encourages, is how all three, despite their different origins, different primary goals, different levels of component intelligence, all converge on these fundamental design principles: modularity, interaction, and autonomy.
It's like different engineering disciplines discovering similar laws of physics for building complex, robust systems.
That's a great way to put it. It's about finding effective ways to manage complexity, and these principles seem to be key.
Okay, let's break that down again comparatively this time. Modularity. We see cells as these isolated, independently deployable workload replicas.
Right. Infrastructure-level modularity, focused on isolation and deployment.
Then FBP processes are reusable components focused specifically on data transformation.
Application-level modularity, focused on data flow and processing logic.
And agentic agents are specialized, often intelligent entities, each with a defined role or capability.
More behavioral or cognitive modularity, focused on tasks, skills, and goals. So different kinds of modules, but modularity nonetheless.
Right. And interaction. Cell-based systems rely heavily on that thin routing layer, routed APIs, maybe messaging, between cells, aiming to minimize it.
Yes, carefully controlled, infrastructure-mediated interaction.
FBP uses data packets, those IPs, flowing through bounded capacity connections between defined ports.
Data-driven interaction, mediated by the network definition and the scheduler, with built-in flow control.
And agentic systems have that much wider, more diverse toolkit for interaction, direct messaging, orchestration, shared memory, tool use, structured protocols, even chat.
A much richer, more flexible, and potentially more complex interaction landscape, reflecting the higher autonomy and cognitive abilities of the components.
And finally, autonomy. For cells, it's primarily operational independence. Each cell can function, fail, scale, and be deployed on its own.
Infrastructure and operational autonomy.
For FBP, it's the asynchronous execution of processes. They run independently when data arrives, managed by the scheduler.
Execution autonomy driven by data availability.
And for agents, it's that more inherent cognitive or behavioral autonomy, the ability to perceive, reason, make decisions, act on goals, and potentially learn.
Right. A much deeper, more goal-directed form of autonomy.
But despite these differences in how they implement these principles, the overarching benefits seem remarkably consistent across all three, based on the source.
They really are. They all aim to manage complexity by breaking things down. They all aim to improve resilience against failures, though through different mechanisms. They all provide paths towards scalability, and they all generally enhance the maintainability and reusability of the system's components.
It's fundamentally about decomposition, divide and conquer, and then carefully defining and managing the collaboration, the interaction between the resulting parts.
Exactly. And that comparative summary table in the source really drives this home effectively, laying out the core module, the nature of modularity, the interaction mechanisms, how autonomy is expressed, and the primary system-level goals for each paradigm side by side. It really crystallizes both the parallels and the unique flavors of each approach.
Yeah, that table's really helpful. Looking at it, what other deeper commonalities or distinctions stand out?
Well, one thing that becomes apparent is almost a spectrum of component intelligence, maybe. And that seems to correlate with the complexity and flexibility of their interactions. Cells are generally reactive. FBP processes perform deterministic transformations. Agents have, or can, simulate cognitive abilities.
And with that increasing intelligence or autonomy, there seems to be a potential trade-off with the rigidity or predictability of the overall architecture.
That seems fair. Cell-based and FBP systems tend to have more prescribed, predictable structures and interactions defined at design time. Agentic systems, particularly multi-agent systems, have much more potential for emergent, sometimes unpredictable behavior arising from the complex interactions of autonomous components at runtime.
That makes sense. More freedom, potentially more chaos if not managed well.
Right. Another subtle distinction is the role of the environment. For cells, the environment is mostly about isolated computing resources and network routes. For FBP, the environment is the network and the streams of data flowing through it. For agents, the environment can be much richer and more dynamic, encompassing other agents, external tools, data sources, maybe even the physical world for robotics. This definitely shapes the nature of their autonomy and interaction.
Fascinating distinctions. Okay, so looking ahead, wrapping this up, what are the key design considerations people need to keep in mind for each, the major challenges, and where do we see these paradigms heading?
Well, each paradigm brings its own critical design decisions. For cell-based systems, as we discussed, it's all about nailing that partition key selection and getting the cell sizing and boundaries right. Get that wrong, and you undermine the benefits.
Okay, for FBP.
For FBP, the focus is really on designing those reusable, well-defined process components and structuring the information packets effectively. Good component design is key to leveraging FBP's modularity.
And for agentic systems.
Their key considerations include carefully defining the roles and responsibilities of each agent, establishing effective communication protocols and languages between them, designing robust orchestration mechanisms to manage their collaboration, and, crucially, selecting or providing the right tools for them to act effectively.
Beyond those specifics, there are broader considerations too, right? Like ensuring the resilience and scalability of the cell router itself.
Absolutely. That router is critical infrastructure. And for FBP, there's the challenge of that initial mindset shift for developers and the need for good tooling, which historically held it back somewhat.
And for agents, the ethical considerations around autonomy and decision-making seem huge.
Definitely. Trust, safety, alignment, bias. These become major factors as agent capabilities increase.
And what about the challenges in actually adopting and managing these systems once they're built?
They each present challenges. Cell-based systems can introduce significant operational complexity. Managing potentially hundreds or thousands of cells requires sophisticated automation and observability. That cell router, if not designed and scaled properly, can become a bottleneck.
Right, FBP.
With FBP, besides the paradigm shift, managing and debugging complex, large-scale data flows can be difficult, especially without excellent visualization and tracing tools.
And agentic systems.
The coordination overhead between many agents can become significant. Managing potentially unpredictable emergent behaviors is a major challenge. Ensuring the security, reliability, and trustworthiness of autonomous agents, especially if they interact with external systems or sensitive data, is critical. Scaling the interactions between large numbers of agents efficiently is an ongoing research area, and designing effective human-agent interaction and collaboration is also crucial.
So non-trivial challenges across the board, but the source also hints at hybrid approaches, combining these ideas.
Yes, and that's really exciting. There's huge potential for cross-pollination. Imagine agents that use FBP internally for complex, structured data processing tasks, or running FBP networks or agentic systems on top of a robust, scalable cell-based infrastructure.
You could apply interface concepts from cells or FBP to how agents interact with their tools, maybe?
Exactly. Or use orchestration ideas developed for agentic systems to dynamically manage cell life cycles, or reconfigure FBP networks on the fly based on system load or goals. The boundaries could definitely blur in interesting ways.
And looking further out, what are the emerging trends?
Well, the source suggests we'll likely see increased adoption of cell-based architectures, probably with more intelligent adaptive control planes managing them. FBP might see a resurgence, especially integrated with low-code, no-code platforms, or finding new niches in edge computing where its data flow model fits well.
And agents. It seems like that's where the fastest change is happening.
For sure. Fueled by LLM advances, we're likely to see rapid progress in agentic systems, more robust frameworks, better techniques for continuous learning and adaptation, significant focus on safety and alignment, development of multimodal agents that handle text, images, audio, and perhaps even more personalized agents tailored to individual users.
One common thread that seems to run through managing all these increasingly complex systems is the importance of that management layer.
Absolutely critical. Whether you call it the control plane or cell router in cell-based systems, the scheduler in FBP, or the orchestration layer in agentic systems, as the components themselves become more distributed and more autonomous, the intelligence and robustness of that coordinating layer become paramount.
And that mindset shift you mentioned keeps coming up. It's not just about new tech, but new ways of thinking for developers and architects.
Definitely. Moving towards data flow thinking for FBP.
Yeah.
Understanding workload granularity and failure domains deeply for cells, and embracing a degree of uncertainty and focusing on goals and constraints rather than explicit steps for agentic systems.
It also sounds like we're seeing a blurring of lines between design time configuration and runtime adaptation in these more dynamic architectures.
Yes, systems are becoming less static, more capable of adjusting themselves based on conditions, which makes the initial design phase more about setting up the framework for adaptation.
And underpinning all of this, the source stresses the inescapable need for advanced observability.
Cannot emphasize that enough. Comprehensive logging, detailed metrics, distributed tracing are table stakes. But for agents, we might even need ways to understand their reasoning processes. Without deep visibility into these complex, distributed, often autonomous systems, operating them reliably becomes incredibly difficult, if not impossible.
Absolutely. Traditional monitoring just won't cut it.
Not for these kinds of systems, no.
So, to bring it all together then, it seems crystal clear from the sources that this underlying focus, this convergent evolution towards modularity, interaction, and autonomy is really a fundamental strategy. It's key to designing and building systems that can actually handle the ever-increasing complexity we face in modern computing. Systems that provide the resilience we desperately need, systems that can scale, and systems that can even start to exhibit intelligent, adaptive behaviors.
It really is a fundamental engineering approach, isn't it? Like you said earlier, it's divide and conquer applied across multiple levels of abstraction, from the bare metal infrastructure all the way up to sophisticated AI reasoning.
And as we continue down this path, it sounds like mastering the interfaces between these increasingly independent, interacting, and autonomous components, the technical interfaces, the semantic interfaces, maybe even the ethical interfaces, that's going to be absolutely crucial for unlocking the full potential of these powerful design philosophies.
Precisely. It's not just about getting them to talk, but ensuring they understand each other, cooperate effectively, and operate within appropriate boundaries and towards desirable goals. That interface management is key.
Well, this has been a truly illuminating deep dive. It really connects the dots between these seemingly separate trends, and it leaves me with a final thought, something for you, our listener, to mull over. As our systems become more and more composed of these independent, interacting, maybe even intelligent components, how will our fundamental understanding of things like system failure or responsibility or even what we consider system behavior need to evolve? It feels like we're entering new territory there. Definitely something to keep exploring. Thanks for joining me for this fascinating discussion.